last chapter is change of variables in triple integrals. We already seen how we can calculate the triple integrals on previous section, and also here we will talk about cylindrical and spherical coordinates, of course, for triple integration. If we just remind the change of variables as x as a function of uv and y as a function of uv, it allows us to evaluate the double integral over uv plane, such as if you have the double integration of gxy over d, then you can evaluate that double integration over s in that way. Of course, you have to calculate here the Jacobian determinant. Okay. Then after completing the Jacobian, you have to take the absolute value of the Jacobian to get dA in terms of u and v. So that is, if you remember, this one is the transformation of x as a function of uv and y as a function of uv. And also, let's remind it, this transformation maps the region S on the uv plane to D on the xy plane. So this one, this change of variable we have seen for double integration, and now we will see the change of variables in triple integrals. Also, it will be same as the double integration if we consider here, of course, the variables as a function of three variables such as u, v, and w. Of course, you will represent y and z also in that way. And supposing that this change of variables transform the domain S in three-dimensional space here, of course, in u, v, w space, to the domain R in the x, y, z space. So on R over 3. Let's remind it again, for triple integration, the function is a function of three variables, and the region, the integration domain, or is a region in R over 3 in three-dimensional space. So that is why we can only sketch the figure of integration domain for triple integration. Then the triple integral in Cartesian coordinates, which we already defined as here, equals to triple integration of f x as a function of u, v, and w, also y and z. So you try to write f x, y, z in terms of u, v, and w times the absolute value of Jacobian times du, dv, and dw. Here represents dv in that way. So here is dv, right? So this is fx, y, z, dv. And here, this one, after you change the variables, this one represents dv. Of course, here again, this is the Jacobian determinant of transformation that we have, and which will be now, if you write this Jacobian determinant, which will be the determinant of that 3 times 3 size of matrices. So the first row will be the partial of x with respect to u, the partial of x with respect to v, and the partial of x with respect to w. Then after that, the second row is the partial derivatives of y with respect to u, v, and w respectively. And the last row, will be the partial of z with respect to u, v, and w. Of course, when you take the integration, here, triple integration, you need to take the absolute value of that Jacobian determinant. Okay, so we need to take the absolute value of Jacobian, that one, the Jacobian determinant. If we start by a simple example here, A, B, C, if we take those as positive values, and if we try to find the volume of that ellipsoid, which can be represented by this inequality, then the volume equals the triple integration of E, right? So if you just take the function as 1, and we have seen that represents the volume of that ellipsoid. So the transformation that we will use is like that. So we take x as a times u, y as b times v, and z as c times w. So it will transform, that transformation transforms the ellipsoid, sorry, the ball to the ellipsoid. So the ball S will be u square plus v square plus w square smaller or equal to 1. So it will transform that unit ball to the ellipsoid. We need to calculate the volume. Okay. Birimizin mikrofon açık kaldı galiba arkadaşlar. Then, of course, for the last second step, we need to take the Jacobian, find the Jacobian determinant. So that means you have to find the partial of x, y, z with respect to u, v, and w. So with this, so for this transformation, then the first row will be the partial of x with respect to u, so this is a, and the other partials are 0, because you take v and w as any constant then. And the second row will be the partial of y with respect to u, so that will be 0. The partial of y with respect to v will be b, and also the partial of y with respect to w has to be 0 for this transformation. So the last row, where that is c times w, the last row has to be 0, 0, c. So when you calculate the determinant of that matrix, that will be, since the just you have non-zero items on the diagonal and the rest is 0, then that will be directly defined by the multiplication of those items on diagonal of the matrix. So it will be A times B times C. Also, when you calculate, you will see it is the Jacobian is equal to ABC. So the volume, if we try to write down the volume of ellipsoid, so which can be represented on Cartesian coordinates in that way. So on S, this will be equal to 1 times the Jacobian, right? So if you can, you should directly write the 1 as 1 here, even for this transformation, right? And then you need to write the absolute value of the Jacobian, so which will be, since A, B, and C are all positive values, so it will be A times B times C, so this is the Jacobian, and du, dv, and dw. So actually here, this one represents d of v. So since A times B times C is any constant, so you can write it B for the integration, and that will represent the triple integration of 1 over S, which will be defined by the volume, so which is equal to volume of S. So we can calculate the volume of S, where S is that unit ball or the unit sphere, you can say. So which will be 4 over 3 times pi times r cube, since r is 1 here. From r cube you have 1, so that is why the value or the volume of ellipsoid has to be equal to 4 over 3 pi A, B, C. Okay, so this is the volume of S times A times B times C, which will give us the volume of the ellipsoid. So this is the first transformation that we have. So here we will have different transformations which we will see as cylindrical by cylindrical coordinates and then by spherical coordinates. We have seen the polar coordinate, so there we try to write a point on on a circle in on xy plane or in terms of r and theta. So you can represent any point on xy plane by coordinates x and y. Also, you can write any point by those coordinates r and theta. So we will use cylindrical coordinates for in triple integration. So a point in three-dimensional space, so that will represent a point in our integration domain as r, theta, z. So in a Cartesian coordinate, you can represent any point in three-dimensional space as x, y, z by those coordinates, and in cylindrical coordinates you can represent any point by the coordinates r, theta, and z. Here r and theta are the same r and theta that we have seen for polar coordinates. polar coordinates of projection of any point on xy plane. And so r here, if you remember, we take r as the distance between here in 3-dimensional space. It is the projection of P on xy plane and the distance between the origin and that point. So r has to be greater or equal to 0, and theta is in between 0 and 2 pi, so as in polar coordinates. And the transformation for cylindrical coordinates will be like that. So this one you already know from polar coordinates, that transformation. X equals r times cosine theta, y equals r times sine theta, and we take as z here for cylindrical coordinates as z. So in particular we can say z remains the same. So that is that distance is z. So this will remain the same. So the Jacobian for this transformation or cylindrical coordinates will be the determinant of this 3 times 3 size of the matrix. So if you compute this determinant, you will get r, which we know it is greater or equal to 0. So when you take here as an absolute value of r, dr, d theta, and dz for dv, so it has to be r. You can just write it as r since it is greater or equal to 0. And after using the cylindrical coordinates, the integration over r of fxyz will be equal to the integration of f in terms of r, theta, and z times r times dr times d theta times dz, which is dv in terms of r, theta, z over s. So it is, we have the same steps. You can say that we have same for polar coordinates, but here we are dealing with, of course, the functions of 3 variables. So, and also the bir tane açık kaldı galiba arkadaşlar. Bir mikrofonumuzu kontrol edelim. Çünkü sesler geliyor arkadan. Ne dediğimi unuttum. Bir saniye. Okay, so for polar coordinates we have seen in the transformations, and here the thing that we have for cylindrical coordinates, the domain, since we are dealing with the triple integration, we need to write down in any p in 3-dimensional space, which will be our integration domain on cylindrical coordinates. Of course, after you have this transformation, you can change the integration order here. So you can modify the integration order when it is needed. So if we start by the example here, So we try to sketch the region. Then we try to express the triple integration in cylindrical coordinates. So from that representation of the triple integration here, we know all the limit of integrations. So we can write the limit of integration for z. Arkadaşlar bir mikrofon açık kaldı da ben dağılıyorum. Bir bakarsanız mikrofon. Tamam. Sanırım buldum. And also the limit of integration for x is from minus square root of 4 minus y squared to square root of 4 minus y squared. So this is the limit of integration for x, and y is in between 0. So this is the last variable here. So from 0 to 2. So this is the r, which is the integration domain. And now we will try to sketch that region first. So the limits of the outer and the middle integrals, so which represents y and x, represent respectively, determine the projection of r. Of course, it will determine the projection of the integration domain on xy plane. So if you just look at those two, those two, then those by using those two inequalities, you can sketch the projection of r, the integration domain, on xy plane. So if we just sketch that inequalities, then it will represent that shaded area on xy plane, which is a half of a disk with radius 2. And from the last inequality, we see that r is bounded by above z equals 2 plane. So this one here is 2, and the plane through here, which passes through here, is z equals 2 plane, and it is bounded from below with that equation, which represents the cone, this cone, this one. So we know the projection of r on xy plane is that half circle with radius r. Then by using the boundaries of z here, we can say the integration domain, or the region r, is that half, shaded half of cone. Okay, so this is that shaded area is the integration domain r, integration region r. So in order to write the given integrals, triple integral in cylindrical coordinates, of course we need to express the region in cylindrical coordinates. So by using the same method for polar coordinates, you can find x and y boundaries in terms of theta and r, and r and theta respectively. So r will be in between 0, between 0 and 2, and theta is in between 0 and pi. So let me just draw here, maybe. So here, this will be theta. So theta will be in between 0 and pi, and z is in between. So here will be square root of r square, because by using the cylindrical coordinates you can get x square plus y square equals r square. So here will be r, this one, will be r, and here is constant, so it will remain same as 2. So that means now we write r, the region, the integration domain, in cylindrical coordinates. So now it is the only thing you need to find, to write down the function in terms of r, theta, and z. So you write the boundaries, z boundaries, r and theta respectively here, and I don't know if it is given an example. Let me see. So this is okay. This is given for any f, but you can try to evaluate as assuming f is x square plus y square. So here the function in terms of r, theta, and z will be the r square. So you try to find out the triple integration over r in cylindrical coordinates of r square. So it will become r times, r square times r times dz dr d theta. So it will be r cubed times dz dr d theta. So you can just find that triple integration assuming fx,y,z as x square plus y square in that way. So the last system of coordinates that we will use for transformation is spherical coordinates. So in this case, now we express any point P on Cartesian coordinate system x, y, z by rho, phi, and theta. So here rho is the distance of P to the origin, so that will be rho. This is rho. And phi is the angle made with positive z-axis. So this is the phi, and theta actually is the same angle as in cylindrical coordinates, so we can say as in polar coordinates. So this is the angle theta. And we call rho phi theta as cylindrical coordinates of any point, and we will relate the Cartesian coordinates by that transformation. So x is equal to rho times, of course it comes from that sketch that we have here, x is equal to rho times sine phi times cosine theta, and y equals rho times sine phi times sine theta. Z equals rho times cosine phi, and theta is in between 0 and 2 pi as in polar coordinates. Rho is in between 0 and pi. Let's remind again, rho is the angle with the positive z-axis, and rho is the distance, so it is greater or equal to 0. So by this transformation we can get rho square is equal to x square plus y square plus z square. It is similar that we have for cylindrical coordinates and polar coordinates for r, which was the distance again between the point and the origin. So here it is represented by rho, so it will be rho square equals x square plus y square plus z square. Of course, we need to find the Jacobian determinant of that transformation, so which will be that 3 times 3, the determinant of the 3 times 3 size of matrices, which comes from partials of x, y, and z with respect to rho, phi, and theta. And if you compute that determinant, you will get rho square times sine phi. So this will be this will let us to get dv as rho square sine phi d rho dp d theta in cylindrical coordinates. So for example, if we try to evaluate that triple integration over R, where R is the upper half of the unit ball or the unit sphere, so we let which is represented by x square plus y square plus z square smaller equal to 1 and z greater or equal to 0. So that restriction makes that sphere as half of it. So we need to express now the region R, this half ball, in spherical coordinates. So that will, if we just imagine, and I don't know if we have the sketch here. No. Okay. So we need to express the half of the unit ball or unit sphere in spherical coordinates. So if you imagine the half unit ball, then the theta will be in between 0 and 2 pi. Since it is half of that ball, phi will be in between 0 and pi over 2. And since here the radius is 1, so for spherical coordinates, the rho will be in between 0 and 1. So now we can write triple integration in terms of rho, phi, and theta. So we need to write the function of x, y, z, which is e over x squared plus y squared plus z squared over 3 over 2 in terms of rho, phi, and theta. So which will be, since here so here is rho square, so that means fxyz equals e over rho over 3 in terms of spherical coordinates. And we already seen that the Jacobian is rho squared times sine phi. So now the rest is just a simple integration here by starting by the inner integral. And for the last step, you need to have that substitution where you let u as rho over 3, and then you can calculate this integration on spherical coordinates in a of course quick way. So the last example includes Cartesian coordinates, cylindrical coordinates, and spherical coordinates. So we try to we try to express the triple integral of any function fx, y, z. So it is we will represent as any function fx, y, z over R, where R is the region lying above the cone and inside the sphere. That one. But we just focus on the sphere. It is represented by x squared plus y squared plus z minus 1 over 2. So z minus 1 squared equals 1. So which means the center is the point with coordinates 0, 0, 1. So here is the center of that sphere. So here you can see the sketch of R, which is the shaded region. And the sphere, for the second step, we try to find the intersection of those two, the sphere and the cone. So this is so this can be found just by plugging x squared plus y squared equals z squared in the equation of the sphere. So if you just compute that equation, you can find z as z equals so it will be x squared plus y squared equals 1 and z equals 1, so which will be the circle here. So that one will be the intersection of that sphere and the cone. And now we can express that region R in Cartesian coordinates. So x, the x values in between, or if you just project that area, that circle on xy plane, you can see the region for x, or the boundaries for x and y. So this will be minus 1 smaller or equal to x, smaller or equal to 1. So the boundaries for x are minus 1 and 1. And the limit of integration for y will be, again by looking on the projection of the intersection, it will be, the lower limit will be minus square root of 1 minus x squared, and the upper limit will be square root of 1 minus x squared. And for the limit of integration with respect to z, if you just come across the negative side of z, the first, let's say, function that you have here will be the lower limit for z, so which is square root of x squared plus y squared, and this one will be the upper limit, so which is the sphere, but you have to write that sphere in terms of z, so you need to write it as z equals 1 plus square root of 1 minus x squared plus y squared. So that will be the upper bound for z. So after you write that limit of integrations for x, y, and z, now you just write here the z, it is not any function, sorry, I was wrong, it is z. So the function is z, fxyz is z, so it will be fxyz, which is z, times dz dy dx, which is dv, and you can start by writing the limit of integration with respect to z, then after that with respect to y, and then with respect to x. So this will be the triple integration of the function z over r in Cartesian coordinates. Now we will try to express the same triple integral in cylindrical coordinates. So just by looking on the sketch, we need to find the theta, r, and the z. Z can be found by using, actually all of them can be written here. So as we said, the projection of the intersection here will represent this unit circle, right? So it will be on cylindrical coordinates, any point that can be represented by r and theta. So on cylindrical coordinates, r, it will be in between 0 and 1, and theta will be in between 0 and 2 pi. So when it comes to z, you can write it from here, the Cartesian coordinates, from here. So after you use the cylindrical coordinates, so the lower limit becomes square root of r squared, so which will be r, and the upper limit becomes 1 plus square root of 1 minus r squared. So this will be the limit of integration in cylindrical coordinates with respect to z. So after that, we will not compute, just we will express the triple integration over r in terms of are theta and z, so on cylindrical coordinates. So the only thing you need not to forget is the Jacobian. So the Jacobian is r, as we found out. So here will be f x y z, which is z, times the Jacobian r times dz, dr, and d theta, and after all we will write the limit of integrations with respect to z, r, and theta. So it is the integration of f over r in cylindrical coordinates. For the last step, so for the last question here, we will express the same region in spherical coordinates. So first we can directly observe the theta by using the cylindrical coordinates. So we have these already. So those are the same thetas. So you have already that limit of integration for theta. And also we can directly write the lower limit for phi, which is 0. This is the angle with positive side of x-axis, sorry, z-axis. So the upper limit of phi is determined by the cone. So let me just again open the figure here. So that will be determined by this cone we have here. So since the cone makes a constant angle of pi over 4 with positive z-axis, positive side of z-axis, we have as a limit of integration for phi from 0 to pi over 4. So in other words, you can say the cone that equals square root of x squared plus y squared is described by phi equals pi over 4 in spherical coordinates. So this is the angle here. So this can be 0 to pi over 4. And the last thing we need to write is the limit of integration for rho. So the smallest value of rho has to be 0, and the upper limit here is determined by the sphere x squared plus y squared plus z squared, plus z minus 1 square equals 1. So this is the spherical coordinates that we have seen, and to try to find the upper limit we need to compute the equation of sphere by this change of variables. And if you just write it again as x squared plus y squared plus z squared equals 2z, and you can see our cylindrical coordinates. Here will be rho square, this part, the left side of the equation, and from the other side, right side, it will be 2 rho times cosine phi, so which means rho equals 2 times cosine phi, which is determined by the sphere we have, and also using the change of variables in spherical coordinates. So this will be the limit of integration for rho with respect to rho. So after all, you need to just write the function, which is z here. So z is rho times cosine phi in spherical coordinates. So rho times cosine phi times, and from the Jacobian, let's see it again. Let me see. Okay, for Jacobian you have rho square times sine phi, so which will be rho times rho square times cosine phi times sine phi. So you can write it as rho over 3 times cosine phi times sine phi. So this will be sine phi times d rho d phi d theta. So this will represent the f times dv in cylindrical, spherical coordinates, and we already found the limit of integration with respect to rho, phi, and theta. So you can express the triple integration over r of the function z in spherical coordinates. And here about the computation, the last one, so the last integration that we have is the one which is easy to compute. So you can just find it, this one, so this one. So you can compute and find that as 7 pi over 6. So this is spherical coordinates and cylindrical coordinates for system of coordinates in 3-dimensional space. The steps are the same that you need to find if you have the change of variables. So the one that you always need to compute is the Jacobian determinant, of course. So the variables can change here. So the UV can change in terms of the coordinates that you use, of course, but the steps are the same that you have find for double integration and also for triple integration. So that is to compute the Jacobian determinant and to write the function in terms of the change of variables that you have. And after all, for the last step, you need to find the limit of integration, and then you can just change the integration order to that you to compute the triple or the integration in general in a quick, in an easy way, let's say, to help you to compute the integration. So this is all we have for triple integration also for this semester. Any question until here? Do you have?